All right, yeah. So yeah, like I said, section 18 is like a huge section. it's not an easy one just to go through. It's going through statistical distributions. Like they first talk about a lot of like what is statistical distribution, different parts of it, and then saying different distributions themselves. So usually I kind of split this up into two parts of us just talking about statistical distributions in general and how these things kind of work. So I'm going to share my screen so that way you can kind of see what I can see. Is that the right one? Yeah, okay, cool. So you should be able to see statistical distributions intro. And before actually, I lost my screen, sorry. My windows get all moved around when Zoom shares my screen and everything. But so this notebook, and we'll talk about this one in a second, just so I have it for my students and stuff. It's on this resources on GitHub. And we're going to look at not statistical modeling, sorry. We're actually looking at probability in stats. And we'll look at specifically statistical distributions. We'll be looking at these, where is it? These two notebooks. So this intro is what we're going to talk about first. And then if we get to it, this guy over here. I'm going to go ahead and send it through you on the Zoom chat. Michael, since you are here. So that way, if you want to, you can go through it later or, play around with it and stuff like that, where there's code.
Is there any way you could send it to me in Slack?
Yeah, I can do that.
So that it won't go away.
Yeah. And, I'll go ahead and put it on the main channel too. I'll just put it in that thread where I announced the time. Sound good?
Okay.
Excuse me. Okay. Some allergies. Repo from today. Ooh. Excuse me. And there we go. Okay. So I just went and put it on there so you can grab it from there and it won't go away. All right, cool. So yeah, so let's go right into this because there's a lot going through. So just note that I'm just importing a bunch of practical stuff. You'll notice like Pandas, NumPy, probably Seaborn, Matplotlib. We'll also have this SciPy. I'll use SciPy stats more than I use like stats models. And I'm importing this kind of special package Skewed norm, which will help us discuss about like skewness and stuff. So first thing to know is how random numbers work like in like Python, in computer science. They're really not real random numbers. They're really called pseudo random numbers, meaning that they're random enough for what we do, but you should be careful to know that they are not in fact random. They're actually produced in a sequence where you could reproduce them every single time. So the way we kind of do this is we produce like a seed. So we're actually using NumPy here. I don't need this again, but NumPy has a random kind of package built into it. And we can actually pass what we call a seed. And that seed basically says, all right, here's your seed to start off with a random number. So in this case, you can give it whatever number you want. In this case, I put 27. So what this means then is that when I run this now, this random, this np.random.randint, this will pass me, we'll find an integer, well, 5 integers between 1 and 10. So you can see here, I'll get 5 different integers. I ran it once. If I run it again, I'll get a new 5 different integers. So you can see here, I can run this over and over and over again. However, if I were to go ahead and do a restart, so let me just do a kernel restart. So now this basically clears out all the memory. So if I tried running one of these, for example, let me just show you what that looks like. There we go. So if I try running one of these guys, it'll say, oh, you don't have that package. Oh, wait. Sorry. Did I not do a restart? That was trippy. Huh. That's never happened to me before. Okay, let me do, all right, so remember this guy right here. So this is the actual output that we had at the beginning. This is what I was trying to show. And I'll do a kernel restart now and clear output. Now I should be able to run np.randint. What is going on? It's not supposed to do that. That's really weird. Anyway, okay, if I run this now, I should get the same answer, 49991. So the reason why this is important to put a seed here is that if you want to reproduce the same randomness, so someone else can reproduce it, it's good to put a seed. Otherwise, it'll try to figure out a seed for you, and people might get different answers. So you'll see me kind of use random to generate some distributions and stuff. But if you want to get the same stuff, make sure you do this seed of whatever they have originally. And it's good practice. Make sense?
Yeah, you can reproduce it. It's not really random. like some random things use like the time from your computer and like some weird stuff, but then they stopped doing that for some weird reason.
Yeah, you still can do that. So you can, it still actually does this. If I don't give it a seed, it can actually use other aspects of like your computer mouse and stuff like this. The reason why we actually pass a number is just so we can reproduce that same distribution. So we know the code works and not just it randomly worked. That's why you'll see seed happen a lot.
Okay.
Mm-hmm. There are some really kind of trippy stuff. For example, I think, I forget the company, they actually use lava lamps to seed their numbers and stuff like that, to actually give real randomness and stuff like this. So you can do some really kind of funky stuff to make it as random as possible. Cool. All right, so let's kind of get right into it, right? So showing distribution. So this is a basic distribution, a normal distribution, and we can actually go ahead and create this with mu and sigma. So that mu part basically is just going to be our average, sigma being our standard deviation. So you'll see sigma represented with this right here. It's also related to our variance, but it's like basically this sigma squared is the variance. We have n equals 5,000, so that says how many samples we're actually going to have. And we can actually generate a normal distribution from NumPy called mu sigma np. So now if I actually go ahead and try to show this distribution, you'll see it's just a list of numbers. Okay, and those numbers basically are distributed, saying the average, if I were to do the average here, you will see that the average would be about 14 because I put in mu, which is our average. So if I do this now, you see it's about 14. And then you should see, hopefully, our standard deviation is 2.8. So if I do standard deviation, STD, you'll see it's about 2.8. And you can see here about here. Okay, so this is, you can see all these different parts. If I actually did like how long it is, like how many things are, there's going to be 5,000 different items. And you can see 5,000 items. So this is just building our distribution up. Okay, so now I can actually go ahead and plot some stuff out. So I'm just using Seaborn here. I'm basically plotting out a distribution plot of those numbers. I'm going to show mu, which is going to be our average, is what we should be, and then mu plus sigma, which should be our average plus the standard deviation. And so we see this now. We can see we have a pretty good, nice normal curve right here. So that's a disk plot. And then that red line in the middle here is going to be our average. And then these two green lines on the side here is one standard deviation above, one standard deviation below. And this is kind of generally how you'll see a lot of distributions plotted out. But note that it is random, so it's not going to be perfectly along this line. As we increase the values in this, it'll get closer and closer to an actual distribution, which I think that might be too many. Good. You can see it gets very, very close to the actual distribution of a normal curve. If I have a lot less, you'll see that the standard deviation, let's say we do 550, you'll see here, it won't be quite normal. There's some randomness in there. So you'll see it's a little skewed and stuff like this. And so this is really like how we can generate some statistical distributions. But in general, we want this nice normal curve. That's what we like to see. Okay, cool. Good so far?
Yeah.
Okay, so next we get into a whole bunch of statistical distributions. So we're going to talk about like PMFs, probability mass function, CDFs, and PDFs, cumulative distribution functions, probability density functions. These parts are basically different ways we can kind of visualize our distribution of data. So really what we're trying to do is we're taking all this data, all these numbers, and trying to visualize it so we can see a better like pattern of what's going on. So our first one is our PMF. And you can kind of think probability mass function, meaning like the mass is like hanging from a bar. So you'll see this actually in the curriculum. It's very similar to a histogram. So if you imagine, this is our histogram here. If you imagine instead having a bar instead of individual lines, essentially the same thing here. Makes sense? So
Right. It's just a different way to look at it.
yeah, right. And the big thing you'll notice with probability mass functions versus a histogram, histograms count actually how many occurrences are there, 5, 10, 15 occurrences in this part. And probability mass function will actually basically divide by it, so it's the frequency. So basically you can think of it like, oh, 12% of the values are at this value, or you know, over here it's about 21%, versus saying going what's it called, like just counting up how many there are. I think this is not scaled the way I would expect it, but the point is it would be actually scaled properly. Okay, and I say someone joined us. Hey.
Hi.
Right. So you join us in the middle of it. We're just showing statistical distributions, probability mass functions. Okay, And so we're seeing a probability mass function. This is some code that you can actually use to plot this out. I know it's a lot, right, to go through. So we'll take this one at a time. So the first thing, we'll actually import this. Okay, so this has a special thing collection, which is kind of like a dictionary, like a special dictionary. Just makes it a little bit easier for us to like do some simulations. Of course, we have NumPy and matplotlib, basically so we can do some plotting and everything like that. So first thing I want to do is actually make some simulations. So I'm actually going to roll a die. So you can see I'm going to do roll die 1, and I basically do np.random random int. So remember, that's going to pick a number between 1 and 6, or between 1 and 7. So only 1, 2, 3, 4, 5, 6. And we're going to do that 3,000 times. Okay. So basically, it's like me taking a die and just really rolling 3,000 times until we get, what's it called, that number and everything like that. Okay, and we'll do that for each one. So these two dies, even though we use the same code here, because it's random, they won't be the same exact thing. And then I'll actually make a new variable called sum of dies, which will actually be another array of 3,000 long. And remember, with NumPy arrays, we can essentially just add them together. So the first value in a NumPy array plus the first value in the second NumPy array will be the new value. So this will also have 3,000. It'll just be as if I rolled 3,000 dice, or it would be like I rolled one die, rolled another die, and looked at the two and said, oh, okay, that's my sum, and I record that value. So you can see here, if I roll this now, you can see it's 154, and a whole bunch of other numbers because there's 3,000 of them, and so on. Okay, so now what we can do, we can use this collections, which is kind of like a dictionary, and use this function, which is super useful, counter, which basically what it'll do, it'll go through each one and see the occurrence. So say, oh, there's a 1. Okay, one over recorded, there's 1, 1. Oh, there's 1, 5. Oh, there's 1, 4. Oh, there's 1, 2. You know, and then it'll keep asking, oh, there's another 1. Okay, 2 1s. And it'll add this up. And it makes it a lot easier for us to actually go through. So once we have our actual die for each one, we can record our counter sum for our collection right here. Okay, and I'm just going to there you go. Cool. Thank you. Oh, did you? All right. So now we're actually can show like, okay, like let's see what this looks like. So the sum of dies, right? As you might guess, there's only going to be 2 all the way through 12. And you can see here we have 7, 6, 8, 9, 5, 4, 3, 2, right? There's no 1, there's no 13, and so on. What you expect, okay? And it's basically a dictionary, more or less, okay? But it's a special one called a counter. Right? So now this preps us and ready for us to actually do some interesting things with it. So one thing we have to do, well, we don't want just the count. If I went from here and just plotted, we'll actually get a histogram. That's not really what we want. We really want to have a probability mass function. So what I'm going to do in this part is basically for each one, this is a list comprehension, I go for each plot range, which is basically how big, how many different numbers there can be. Well, it can be a 1, a 2, a 3, 4, 5, all the way to 12. So I'll stop at 12. And basically, I'm saying, okay, for each one of those, see how many times that dot get. So I say, okay, here's the number 1. How many number 1s happen? And divides by the number of times it actually, how many rolls I actually did. So for example, if for this guy right here, I had 557 7s, right? It would basically 557 divided by 3,000, and that would give us this part. And I'm rounding it so that way it's not super big, like long decimal numbers. And I do this for each part. Follow along with me so far, everyone?
Yeah. What is the 0 for the second input?
Oh yeah. So I put this in here so I don't make a mistake. So this dot get is the safe way of getting a number from a dictionary or from a collection. So what it's trying to get k. So it's going to look for the number 12. Well, okay. In some cases, if my simulation is really small or really unlucky, I might not ever get 12. So if I try doing something like, let's say if I go, let's see here, what do I have? Counter sum. So if I do this, I do like number 7, right? I'll get the number. But if I try doing, let's say 13, well, 13 is not in there, and it's going to give me like this part, which is actually really nice. I actually forgot to counter did this. So if this was a dictionary, though, if I did something like, so I'm trying to make myself break. So I have a dictionary here, and I call 13, you get an error. It's like, doesn't exist. If I tried 7, it would work fine. So this dot get part, it allows us to actually, it's like, well, go ahead and get that number I'm asking for, let's say like the number 7, And then if it doesn't exist, give me a return value. For an example, I'm saying, oh, it didn't happen, 0. So this will return 557. But if I put in something like, 27, which doesn't exist, it'll just return 0. Which actually, it turns out I don't actually need this. But if I use a dictionary, it would be useful. So this is a safer way of getting the number. Okay.
Thank
Good
you.
question. No problem. Okay, so now I run this guy right here. And now I can actually start plotting. Yeah, I can actually go see something, right? So what I'm doing here is basically each die. So remember, I did this for each roll of die. So I ran a whole bunch of like 3,000 ones, and then 3,000 with another ones, and I'm going to plot each one. So we'd probably expect this to be about the same size, right? Or like same shape. And you can see here, almost everyone, like, it should be about the same probability of getting each one. That makes sense, right? Is that like, it's about, like, sometimes we get a little unlucky or lucky, depending how you look at it. Sometimes we get number 4. It turns out 4s happen by chance to be the most common one for both of them, but that's just random chance. It really should be about equal. So I was like, okay, cool. This is a uniform distribution, right? More or less. And you can, like, this is where like you could try to look for patterns in here. It's mostly just random. Also note that, remember that each one of this is what we call the probability mass function, is that each one of these is the probability of it happening. So about 16% of the time in this die roll, we got 1, okay? And then about like maybe 17%, we got a 2, and so on. So this is how we can read off the probability directly on here, okay? Now, if we combine these together, so remember the probability mass function for sum is going to be as if I took the very first one and the very first, I have a whole bunch of die rolls for die number 1, a whole bunch of die rolls for number 2, and I take the first die roll for 1, first die roll for 2, add them together, and that's going to be my value. So as you probably can guess, we're probably not going to get the same uniform distribution because there's only one way to make a 2, right? Would be 1 and 1. But there's a lot of different ways to make a 7. We can do 3 plus 4, 2 plus 5, 1 plus 6, right? So we can do a whole bunch of different ways in here. So you'll see that we actually get a distribution that actually isn't uniform anymore. You can see it kind of has this nice shape over here. And underneath here, I have a histogram, which you can see the histogram actually looks very similar, and it should be very similar. Turns out, sorry, scrolled a little bit too much. The probability mass function is just a scaled down version of the histogram. So you actually can see here is that the values are kind of closer to like, oh, this is about 15%. This is maybe like, almost like 17%, maybe 18%. Excuse me, I'm about to sneeze. But basically we have these different parts, and you get the probability from here, but a histogram just shows the frequency of it happening. So you'll hear sometimes people say the frequency versus the probability and stuff like this. And the frequency might actually just be how many times this occurs. Okay, cool. Sound good? Any questions? No? All right, awesome. And you can see here, it took a lot of time just to get to this point right here. But the point is that usually you wouldn't have to simulate the data like I just showed. I'm just kind of showing an example of rolling a die. And you could just go from there. So that's our PMF. So probability mass functions are really useful when you have discrete parts. A cumulative distribution function, CDFs, okay, is another way of showing the same information. It's just, it's a different way of showing it. So if I actually do the same exact data here, this PMF sum, we'll actually see our CDF will look like this kind of staircase going through. And what's going on here is that each step going forward is just including everything. So it's like how many, like for example, when I see number 4 here, it's saying what's the probability of number 4 happening? Or like how many roll dice the sum were actually added up to 4. It's like, well, it's about like 9%. Well, what this is saying is that 4, it's saying how many are at least 4, or sorry, underneath 4. So that's the times you got 1, which are none, but like 2, 3, and 4. So it's adding up to like, okay, we get this many times. So you can see here, that's about almost 20%. Well, that would be as if I added about like 0.8, 0.5, and then like 0.3, right? Which is about 20%, 19%, right? And so I'm adding up all these probabilities, and that's our cumulative CDF, our cumulative mass function. Cumulative distribution function. So we have this right here. You also notice there's some pattern here. So if we have many, many, many like different functions, like for instance, going just 2 to 12, we might have like go through like 1 through like 20,000. This will get smoother and smoother because the steps will get smaller and smaller. But you'll notice here is that the ones that have these bigger steps, they kind of jump up suddenly. Okay, well, those bigger steps, what's going on there is that there's just more of them there's a bigger step each time. If it was a uniform, it basically would be a straight line. It basically would kind of increase, 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 increase. So for example, if I did my PMF, what did I put down? What is it called? PMF die 2. So let's say die 2. That will be basically, their steps will be more or less equal each time. And it only goes up to 6, so that's why it stops right here. But you can see they're more or less equal. But if I go back to the other one, which was our PMF sum, you can see those steps are different sizes. And what you'll usually see, since we usually have many, many different values, and I'm just going to draw a little bit here. There we go. We actually would have these kind of connected together. So you actually would see kind of the shape where like an S-curve. And this S-curve usually means, in that case, if you see something like that, it's usually saying a normal distribution. If we instead had something, a curve that looked kind of like, let's see if I can just draw, I'll just draw on top of it again. Sorry, my little tools got moved over. Okay, if I instead go like, if I saw a distribution that kind of went off like this, and then stepped up like this, what does that probably tell you about these values? Did a lot happen between 2 and 6 based on this red? Yeah, no, right? Basically, it either didn't occur or was very, very small, right? And then all of a sudden, most of the change happened within this part. So basically, the steepness of the line tells you what's the transition. And this is useful basically for us to now make more of a continuous function, which will lead us into our PDF, which is going to be closer to, what's it called? A continuous function, okay? And that's where we get into our probability density function. Right. Any questions on this guy before we leave into that? Cool, thumbs up to understanding. Sound pretty good? Awesome, cool. So probability density functions. So this is probably likely what you actually talk about the most or look at the most. So they're really like PMFs, but they're continuous. So you can see here, this actually, I found this online, is that basically it's a, this right here is more or less our, it looks like a histogram, but you can tell it's not a histogram because the values are super small here, meaning that it's scaled down to probability. And basically this is our PMF, our probability mass function. And you can see here is that it's like, well, this is nice, but if I wanted values, this is 400 to 800, but what if I want to go in between these values? Like if I wanted to get something like 350, well, if I had just this guy, it's not super clear how I would do that. So the PDF basically kind of makes a continuous function. And you can see here, it more or less follows along here. And we'll actually see different ways to generate these PDFs. But essentially what we're trying to do is that all data in the world really is always going to be discrete, right? There's never going to be an actual continuous. You'll never be able to get like the exact in between. If I'm looking for people who are like, let's say 100 pounds versus 100.1 pounds, 100.1.0.1 pounds. You can always go smaller and more discrete. So we want to be able to find those parts. So we actually make this a continuous part. So there's kind of a subtle part in this though, is that we'll always use a range to find the exact number. So one thing is like, we'll always like, how do I say this? So I'm trying to give it, kind of lead you guys into a question. So if I were to kind of like say, okay, what's the probability of landing in this target area? I might say, what's the probability of landing within this area right here? And you can say, oh, it's like a 5% chance if I did it randomly, right? So we can always like make this part. If I made a smaller circle, right? If this is a 5% chance, or let's say if I do it within here, if I do a smaller circle within there, you'd be like, oh, there's like a 0.1% chance you'll hit that randomly, okay? What's the probability of hitting an exact point on the target? Imagine that, like a really small point.
Almost 0?
Yeah, 0, so I see 0. So I used to have, when I was back in physics, a professor used to talk about how when he was doing physics, one of the students would always be the 0 guy. And literally he would just yell out, whenever the professor would ask, like, so what is this value supposed to be? And he would always go 0, because like, usually it's like some kind of leading question like that. And that's exactly right. Basically, to get any one specific point mathematically says, it's a 0 probability, which hopefully kind of makes sense a little bit. It's like, oh, to get that exact point, we could always like, if you were like a cheat and say, oh, you have to hit this exact point. Like, haha, I hit it. And like, well, look, if I go really, really small, you didn't actually hit it. Like, and this is kind of like why we have to kind of marry between the mathematical world and the real world. So we always use a range. We say, oh, find within this range. And that's how we define our probability. And that'll be really important when we do probability mass functions, because that's how we essentially will find our actually probability. So one thing to note too is that, how do I say this? I'm kind of skipping around a little bit, is to find the probability of like happening between like, let's say like 330 right here. Oops, there's my annotate tool. Let me draw. Okay. If I go from here to here, right here, I'll say, oh, that's a probability of, I'll just make something up, like 0.03. Okay, so 3%. Okay, what's really happening here is that mathematically what we're gonna do is find the equation or the function that makes this line, this nice, smooth, beautiful line, and we basically just find the area underneath. So area underneath the curve, and that's how we calculate that probability. So it makes it nice and easy for us to do, because integrals are something that we can like do a lot easier on a computer and stuff like this. So this is actually the reason why. Sorry, I'm trying to clear out my drawing. There we go. This is actually why we normalize this area to 1, right? So what's happening here is that we're actually counting all the areas. So if I count all of the area underneath the curve, well, that's like, it's like saying, what's the probability of happening from here to here? Like, what's the probability of me going between rolling a sum of 0 and 12? Well, it's 100%, right? You'll always get a number between 0 and 12. So that's actually what's happening here, is that we're normalizing it to an area of 1. So just know that whenever you hear probability from the probability, the PDF, basically it's just doing area underneath the curve. And that whole area underneath is just an area of 1. Okay. So this is a good example of like multiple parts. So we have kind of a PDF, a CDF, and a PMF, so a probability mass function. Note that, again, this is just something I found online really quickly, is our histogram. Again, it's really not a histogram. They're kind of not true on its part. This really should be a PMF, but people get confused easily. And you can tell because it really should be about the probability going through and stuff like this. This is the frequency of what's happening, like how often does this happen. So you can see here is that we have our kind of like our, where it says normal, this pink. This is basically just our CDF, just they're, instead of little bars, they're actually like little histogram parts. This guy right here is our PDF. So this is kind of like, it's saying, oh, this is our probability density function, our normalized part, and we'll show how to find these different PDFs and stuff. And then this blue here is our CDF. So you can see here, because it's a normal curve, you can see that kind of S kind of shape, is that there's not much going on. It's still increasing barely. And then as we get in the middle, that's where most of the increase goes through, and then kind of tapers off because there's not many values on the side here. Okay, and so you might see this like all together, but I think this was a good visualization of seeing it all put together, and they're describing all the same data. Okay, cool. Any questions so far about this stuff?
I'm sorry, I think I missed it in the beginning, but what is the difference between PMF and histogram?
Yeah, so a PMF basically is a squished down, like a scaled down histogram. So you'll see here, I think I wrote it right here. This right here is a histogram. This right here is our PMF. And you can see, for example, just count how many occurs. And the PMF basically saying, what is the percentage that's occurring? So essentially we're scaling it down, so this should add up to 1.
Okay.
Cool. All right, so this goes into like our visualizing it. So actually creating the PDF, it depends on how you want to approach this. So the first one is a parametric fit. And when I say parametric fit, all you should think is like, there's an equation, this beautiful equation that we want to fit perfectly onto our data, right? So a parametric fit, for example, is just basically taking the normal curve. We take the normal curve, our bell curve, our Gaussian, our beautiful, beautiful Gaussian curve, and say, all right, our data should look like a Gaussian curve. So we're just going to fit it. We're going to put in the parameters, basically the average, mu, and the standard deviation. Those two values will actually create our normal curve. And we'll talk about that maybe, yeah, we'll talk about that next. So just basically all you need to know is the 2 parameters to actually create this curve. So it's really nice because then it means like, oh, cool, we can just simply just find what the numbers are, input them in, and create our nice curve. Now in reality, like as you can see here, this is using a parametric fit. This isn't close to reality. You can see it looks kind of normal. If I got rid of this black line, it kind of looks normal, but you can see there's definitely some spikes, you know, that could be important. So one thing we can do is something that's a not parametric fit, where we can do something like a kernel density function or a KDF, right? So a kernel density function, and this is where, this is probably like a hard one to kind of wrap your head around, like, why is this working? So the idea here is that we want to take the actual data and make it fit on here. So if I look at like this data over here, what I might do if I pick a color that probably shows up well, yeah, we'll try pink, purple. I might, for example, like kind of make data that's like, well, I kind of want to like incorporate a little bit that goes around here, kind of capture some of those peaks and valleys going through. And that would be closer to reality. Okay, and I'm using the data. Now, in reality, you can't just simply just draw around it. Like the simplest way, I mean, the really simple way to do this is, well, anyone got to guess how I could kind of make it fit closer to the data in the most straightforward way?
Polynomial?
Polynomial? Yeah, that's even more complicated than what I'm thinking. So what really simple, I say connect the dots. You just connect each top. Say, all right, connect dot here, connect dot there, and that would be my probability density function. And that would be like, you know, it's like, it's a crude way, but it would technically be true, right? It's like, that's not super nice because now we have these weird jagged curves, for example, and we, you know, is that what we really want? We want something that's nice and smooth so we can like integrate over it and predict things off of it. That's where our KDF kind of comes through. So our KDF, oops, let's go ahead and get rid of that random line. Okay, so our KDF here, I shouldn't really call it KDF, it's really kernel density. So what we're gonna do basically is we're gonna try to see where, like, how do I say this? The more times like points occur very close together, we wanna say, oh, that's where it's more probability being there. Remember, our shape is describing the probability of it occurring. So these values, for example, there should be a higher peak over here versus over here. There should be some kind of like dip. Nothing almost happens over here. And then it should get taper off right here. So one strategy we can do, like I said, that we could try to connect it together. We could try to like fit like a polynomial, like you said. There's a bunch of ways we could kind of try to create this. So one kind of nice way we can do that's really nice mathematically is we basically create a bunch of normal curves. And so what we say here is basically for each data point, and you can see this, you guys can see those little dashes right here, that represents one data point. And what we can do, as you can see on this side, is we just simply go ahead and draw a normal curve, a nice simple normal curve with centered with the mean at that specific data point. So we basically do that for every single data point going through. And what's kind of nice about this, like, it's not super obvious in the way that we're doing it unless you have a lot of mathematics, is that you can actually add these up very easily. They're basically like wave functions. If you ever have done like physics, waves kind of like either add up or subtract. So what we can do is basically, well, if you have a bunch of wave or Gaussians that are close together like this, these parts will kind of influence each other and be added up together. Versus if there's a bunch of like, you know, slopes right here, it's going to be diving down a little bit. It's not going to add up as much. So that's essentially what happens here with the kernel density function. So you can see they have our different Gaussians kind of drawn over each individual point. And those points right here, there's a lot right here. You can see there's 3 different peaks. Those add up to essentially this larger peak. Versus there's a little peak here, but you can tell like as right here, there's almost like nothing. So there really is a big dive right here. There's might happen, it's not 0, but it's a lot less likely to happen versus maybe another peak here where more points occur. And so this is how we can get a more natural, like mathematically nice, like I say, more mathematically nice function. And what's cool is that we can actually build this function and have an equation at the end of it essentially. And it's a lot easier to kind of integrate and do a lot of mathy things. That's really why we like the normal curve, because we can do a bunch of math on it. Okay, cool. Does that make sense to everyone? Thumbs up if that sounds good. Okay. Any questions? No? Okay, yeah, this is probably the harder one to understand, but just know basically you're using the data to create this nice kind of curve using a bunch of Gaussians. All right, so let me move on to the next part. So you can kind of use this comparison. So this is a nice little example. You can see here is the data right here. You can see the histogram, which is like essentially our CDF, or sorry, our PMF. And you can see here our PDFs, which are 2 different ones. One is that green one, the nice parametric fit. It's beautiful, right? It's got that nice, beautiful curve. It's nice and simple. We can basically describe that whole curve with just 2 values, which we'll see in a second. But you can see it's not quite normal because you can see it's kind of flattens out right here. So we actually have a kernel density, right? And those are the density estimation. So it's not, it might be true, it might not. It's just all based on our data. But because there's a flat end here, basically we see it's close to normal, but it kind of flattens out here and we get this nice function right here that's more descriptive of the data. So we kind of sacrifice that nice, beautiful, you know, simple like 2-parameter fit with this kind of like, you know, something that's more true to the data. Okay, and so you'll see KDEs used a lot more often. Okay, cool. So this leads us into normal distribution, and you've heard me say all these nice things about the normal distribution. It's also called the bell curve, Gaussian. You know, you'll hear all those terms constantly. Basically, the reason why we like about the Gaussian, and I don't know how you guys feel, but this math right here, it's just beautiful. It's singing to me right now. It's nice and pretty. There's just all these constants. There's pi, there's 2, there's e, right? So these are not just numbers. And then all we got to do is we have to know what mu is, which is the mean, and what sigma is. And what's cool is that we just put any value you want in there. Once you know what the mu is, so the mean, and you know what the standard deviation is. If you know those two parts, all you got to do is put that in and say, all right, I want to know the probability of x happening. You put x in there and say, okay, x is in there. Probability of 11.2 happening. Put it in there and boop, y pops out the probability of that happening, which is just awesome. Like, I don't know, it's just a nice little thing. So this is why we'll tend to want to use the Gaussian, because it's very nice. And what's nice is that it turns out most distributions we'll talk about in the future, or I guess Ebony will talk about, and you'll see in the curriculum, the central limit theorem. And you can actually see that we do tend to approach a Gaussian curve and stuff like that for a sample of samples. So it's actually a nice thing for us to know. So also because it's a nice move or a nice like slope and everything, all Gaussians are similar to each other. So we actually have some really quick rules that we can do. For example, the 68, 95, 99 rule. And basically that says is that if you take in, sorry, I'm trying to draw here. There we go. If you take basically the first standard deviation, you have about 68% of the values fall within the first standard deviation. If you got 2 standard deviations, so everything within this area right here, you get 95% of the data. And then if you got to 3 standard deviations, you get 99.7% of the data. And this is where, for example, you might hear in scientific research, for example, to say, oh, past 3 standard deviations, oh, we can say it's significant and stuff like this, is because the likelihood of being out here is so small that it's like, well, that's probably, you know, not just by chance. That's probably something else is causing this, which leads us into the z-score. One thing to note is that I think in the medical field, 3 standard deviations is pretty significant. Like, yeah, like 99.9% is like pretty solid, right? Depending on your field, that might not be good enough. So, for example, particle physics, they have a different, they don't use 3 standard deviations. Does anyone know by chance how many standard deviations they actually use? Yeah, so it turns out 5 standard deviations, it says, oh, that's a significant thing, we should look into that. 7 standard deviations is what we say, okay, that's when we say there's an actual result. And this is because they do so many times over and over that they want to make sure that even by chance, even a 99.9999999% sure, that might not be good enough because they do so many experiments, like literally millions of experiments per second kind of deal. And so you want to make sure that you are finding things because you can find things that don't actually occur. So if you were wondering, like 5 standard deviations would be like right here, 7 standard deviations like right over here. So the likelihood of this happening is really, really small if this is the true thing right here. Okay, so that leads us kind of well into our z-score. So I'm actually not going to go completely into the z-score, but basically just know that your z-score, oops, there we go. Your z-score is essentially how many standard deviations your value x, whatever your x is, from the mean. So if the mean is 12 and it's a normal distribution, your z-score would be, so the mean is 12 and you get like 14 and the standard deviation is 2. It'd be 14 minus 12 divided by 2. So it's basically 1 standard deviation away from the mean. That's really what your z-score is saying. And you can basically do this to compare different distributions and such. I'm going to kind of skip this over because there's a lot for us to go through right now. But know that our z-score will lead us into z-test, will lead us into, what's it called? Our t-test, which is what we'll typically tend to do, because a t-test will be a modified version of this nice Gaussian stuff like that. Okay. All right. So last thing I want to show for Gaussians before I kind of go into a little bit more is there's a nice interactive part from this note, or I linked in the notebook, is you can kind of see where you compared multiple distributions. So you can see here, this is the nice normal standard normal curve Gaussian, basically an average of 0, a standard deviation of 1. And we have our guy over here where we can kind of adjust, for example, our standard or our mean. So notice if I move the mean over, you can see it moves the whole distribution over. So if I have a mean of 4, okay, or almost 4, you can see it's centered at 4 here. If the standard deviation is wider, it means that there's more chance for it to be over there. If the standard deviation is closer to 0, basically it's saying, well, there's most of the values occur within this part. So if I change this sigma, this standard deviation, if I have it closer and closer, you can see 0.25, so I'm really close to 0. Okay, basically means that most of the values occur within this part. So a small standard deviation basically means most of the values occur really close to the mean for a normal distribution. And if I expand it outward, you can say, well, a bigger standard deviation means that it can just reach out very, very far outward. Okay, and then you can see our z-score here. Our z-score basically is just saying, well, if I have this, like, let's say x1, okay, and that's at 3, and let's say our standard deviation is like just 1 standard deviation, well, that means our z-score should be about 1, which is what you see right here. See here? So it's almost minus 1 because it's almost one standard deviation underneath the mean. Our z2 here, which might be another distribution, so you might have another, like, well, let's say x2, let's say be over here, well, our standard deviation would be almost, our z-score would be 2, it's about 2 standard deviations away. And you can use this comparison between the two. You can also say between this green, like between 3 and 6, you can say how much that's actually being calculated. About 80% of the values fall within 3 to 6, which, remember, this right here should be about 68%. So you can see here, it's 1 standard deviation away. If I do 2 standard deviations away, we should get about 95%. And you can see about 95%. So it's a nice little, I thought this was a really great description and the kind of interactive plots. So definitely check that out. I'm going to link in this notebook as well. Okay, cool. So a few more things to go through, guys. Section 18 is a pretty long one. Deviations from the normal distribution. So this is when, for example, this is where you might have seen this, depending on like your first project. You might have seen a little bit of differences. So yeah, you guys have done your first project already. So right here we have our nice Gaussian normal distribution, right? And you can see basically the mean, the median. Remember, the mean is like where the values occur, and the mode are all within there. Usually don't talk about the mode too much, but it could be there. But the mean and median are an important part, symmetric. Now, if you have instead, for example, the skewed distribution. So for example, you see a positive skew. So this might say, we will say there's a skew to the right, and note that the skew is describing where it's pulling towards. So you can see here, it's kind of like if you have this nice distribution and it's getting tugged off to the right, it'd be a right skew or a positive skew. Okay, you'll see here that the median doesn't change very much from that original middle, but the mean gets dragged over really quickly. So we actually say the median's a lot more robust than it is the mean. And you can see the opposite with a negative skew or a left skew. Is it's getting the mean is also getting pulled off to the left over here, but the median's staying in the middle. Okay. So this is kind of like what you'd see if you graphically put this out. There's a bunch of ways you can like measure skewness. For the most part, like you can like measure like actually a number. I think the curriculum actually shows that part. For the most part, it's not, the numbers themselves give you a summary of what you're seeing. The better thing to do, in my opinion, is to make sure you do a visualization, and then you can use the numbers to help guide you in saying, well, how skewed is this data? Remember that like any one statistic, a statistic is a number that we pull out from our data, is in essence a summary of that data. It's only one aspect. I kind of do this analogy where I talk about, like, have you guys ever heard the story where like there's a bunch of blind men and they're like touching an elephant and they're trying to figure out what's in front of them? Like they're trying to figure out if it's an elephant. Well, they don't know it's an elephant. They're just trying to figure out, one person touches like the ear. It's like, oh, it's like a bed sheet or something. And then someone else touches like the tail, like, oh, it's like a broom. That's what you're doing with your statistics. You're basically, your mean and your median, your mode, your skewness, all these parts, you're basically trying to get a feel for what your full data looks like. You're looking to figure out what your elephant is. Okay, so just kind of keep that in mind. Kurtosis is similar. You can also calculate kurtosis. There's actually many ways you can calculate kurtosis, but kurtosis is kind of like skewness in the y direction. So something with high kurtosis, what that looks like, kind of draw this out a little bit. So a normal distribution, like we've imagined, here's a nice little normal distribution, our beautiful bell curve, right? If you have high skewness, or kurtosis, if your kurtosis is high, you basically have a spike here distribution, versus something with low, small kurtosis, you would have it more kind of spread out in this way. So this is deviations from like the standard mean of 0 and standard deviation of 1. So if you have something that deviates from this, this would be saying, oh, it has high kurtosis and stuff. And there's ways to metrically like define this. Again, though, plotting it out, visualizing is probably the best way to go for. For example, we might say, well, we want a normal distribution. People have asked me, how much kurtosis should I be allowed? And it's like, well, it depends on your situation. So any number is not going to be good enough to just report like, oh, I have a kurtosis of 3.2. That means nothing to me. Maybe that's important. Maybe it's not important. Numbers, again, are just giving us a summary and a view of one aspect. But in reality, the best thing to do is to try to say what context does it matter in. Okay, cool. Any questions on those two parts, skewness or kurtosis? Okay, cool. And again, this mathematically, if you check out the curriculum, what they look at through, you'll see the similarity of like variance, which is like our standard deviation. So standard deviation, skewness, and kurtosis. Standard deviation, variance, is by squared, right? Basically how far it's from the mean. It's a squared value. Skewness is a cube value, and kurtosis is to the power of 4. So I guess there's not support for that, but like power of the 4 value. So you can kind of see how they relate together. They're basically saying how they differ, how much the distribution spread out in different directions. Okay, cool. So statistical testing, this is where I'm going to actually skip over this. This is actually moved from version 1. It's moved into a little bit later into module 3. But just know that this is the leading part of statistical distribution, statistical distributions allows us to do more statistical testing. The first part really is a one sample z-test, which is z-score. So it's kind of like, it's not beginner level, but it's like, oh, this is like, we normally don't do a z-test unless we have like a very specific distribution, but it's a good start off to understand what statistical testing is. It's talked about in the curriculum. Basically what you do is you state your hypotheses. This again comes from, this is from version 1's old stuff, so I'm kind of like skipping over it. But if you're curious, there is a video here from Jeff, one of the instructors. I thought he does an excellent walkthrough of walking through like a z-test and see what that looks like. So that is in the notebook as well. It's also in the student resources. I highly recommend if you're curious how to do this, just go and watch that video. Okay. Cool. So that is kind of like my introduction to my whole intro of like statistical distributions. Any questions? No, pretty good. Sound good? Okay. So like I said, section 18 is a beast of a section. There's a little bit more. We still have about like a little less than 10 minutes left. So one thing I want to show apart is basically the different distributions. So we talked about a normal distribution. I kind of hinted at a uniform distribution, right? But there's a whole bunch of different ones. So I'm going to go through this relatively quickly. Most of this stuff, I'm going to be honest with you, you don't necessarily need to have this memorized in any way for, I would say the curriculum, but honestly, even like your career, you will see more that are more common. It's more important to understand that there are different distributions through. And to be quite honest, if I was your guys' instructor right now, like if I had you guys like the next day, I probably would take a little more time to say, okay, we're going to talk about a little bit next time. So just know that this resource is available for you guys on the GitHub repo. What's it called? I'll just kind of go through it really quickly so that way you guys get a little exposed to it. Cool. All right. So again, just reviewing statistical distributions, we saw what that is. Basically, it's summarizing the probability of events that happen. So there's a ways the probability can kind of come out. So one is the uniform distribution. Basically, like I showed, it's like basically if you roll a die, that's a uniform distribution. 1, 2, 3, 4, 5, 6 are all super common, or not common. They're all equal to each other. So basically, the average is just going to be the beginning part and the end part divided by 2. And then our standard deviation, basically the same thing, to divide by 12. You can look up the mathematics of why this happens, but the important part is like you can calculate the mean and standard deviation pretty easily. Should you memorize this? Nah, like you're not gonna memorize that. There's no reason to. Okay, so normal distribution. So this is our beautiful bell curve. So the reason why bell curves tend to happen in just life is because most things in life are just random. And so if you guys have seen this kind of little thing, basically what happens is that the balls start at the beginning, and when he flips it over, the balls kind of hit these different pegs, and they can go basically 50% of the time they go to the left, 50% of the time they go to the right. So going off to the right many times is like flipping coins heads, like over and over and over and over again, and you eventually go to the head. So it's very rare for you to actually go off to the side. But it's more likely for you to go left and right, then left and right, then left and right, then left and right, or right, left, right, left, left, right. So you're more likely to be in the middle. And that's why most of the values fall in that nice little peak over here in the normal distribution. Okay. So some useful equations, we already saw this, is the Gaussian, right? It makes it really easy because all you need to know is the mean and the standard deviation. Sometimes you'll see it written as a variance right here, so you can see it's sigma squared on the bottom here. But basically, as you know those two parts, you got the Gaussian. Or if you have the Gaussian, you can pull out the mean and the standard deviation pretty quickly. So that's a really nice thing to do. Okay, binomial distribution. So binomial distribution, I'm trying to think of like how quickly I want to go through some of this stuff. So this is much more closer to, okay, I'll just describe it. Like, so you would say the probability of getting the number of successes in a given trial. What does that mean? So the way you can phrase this is basically, the way I like to say it is like, let's say I say, I'm gonna flip my coin 10 times, okay? And I wanna see a success for me is getting a heads. So I flip my coin 10 times. What's the probability of getting 5 heads? It's like, well, okay, you can figure that out. You're probably gonna get about 5 heads 50% of the time. What's the probability of me getting like 9 heads? Like 9 out of 10 of them actually getting, you know, heads. What's the probability of me getting only 1 heads, right? And you can probably guess, oh, well, 50% distribution, it's gonna be nice symmetric. But the part, basically each of this K part right here is saying, how many heads do I have? I have, let's say I flip my coin 6 times. How many times, or what's the probability of me getting 3 heads? Probability of getting 2 heads, probably getting 1 head, probably getting 4 heads, and so on, okay? That's what we mean by success. And note that it doesn't have to be 50%, it could be something else. So the way you can find this mean basically is say, all right, the number of times you do the thing, so the number of times you flip the coin, and then P is the probability, so 50%. Well, if I flip my coin 10 times, 50%, my mean will be 5 heads, right? On average, if I did this many, many times. You can also have like the standard deviation. This kind of got funky. There we go. And then you can find this huge point probability. I'm not going to go over this. Basically, it's just saying if you wanted a success in this specific number of tries. So instead of counting how many successes we have within 10 flips, we might say, what's the probability of me getting 3 heads in 5 flips, or 10 flips, or 15 flips, or 20 flips. That's what this is trying to show. Okay? And these are all in the curriculum as well. Cool. All right. Aaron, follow me so far? Okay. So this comes to the negative binomial distribution. So the negative binomial distribution, and there's a nice little GIF, ooh, right? So this is kind of changing things out. This is kind of like, this essentially, the binomial distribution is like kind of like a special case of this. And so the way I kind of describe this is going back to my flipping coins, right? Is I flip my coin, let's see here. I will stop flipping my coin when I get 2 tails, not 2 tails in a row, just 2 tails. So if I get 2 tails, I'll stop. So that's when I fail, right? So what's the probability of me getting 9 flips? So I flip, flip, get tails, flip, 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 tails again. So what's the probability of actually stopping on 9 flips? What's the probability of stopping at 10 flips? What's the probability of stopping at 100 flips? Because I could technically maybe get like a bunch of heads and not get 2 tails until the very end. This is what our binomial distribution, and this is where this like this graphic comes from Wikipedia. Basically, it's adjusting, saying, well, what's your number of successes essentially? Like how many like times you have to fail. So this R is like, oh, if you flip 1 tails, basically the probability of you getting 25 flips is very, very low. But as we kind of increase the number of times we can fail, okay, so we can get like 40 flips, you can see this numbers actually goes higher and higher and higher. Okay, cool. So yes, so I'm sorry, I misspoke too. I said this is the general form. Binomial is a general form of negative binomial distribution. That's wrong. That's I didn't mean that. It's the geometric distribution will be a specific form of this. But basically, you can calculate the mean and the standard deviation like normal. Okay, and again, this is in the curriculum. Geometric distribution. So basically, it's the same as the negative binomial distribution, but you fail 1 time. So once you flip a tail, you stop. So it's basically just a special case. We'll tend to do geometric distributions because sometimes that makes more sense. For example, if you wanted to make a simulation and say, okay, well, how many times does this happen until you die, basically, right? It's like, well, once you die, you can't do any more than this. So that's kind of like why we usually use the geometric distribution a lot more commonly. But negative binomial distribution still exists and is still really useful, but we'll tend to see geometric, the special case, okay? Kind of like our 0 guy. You know, sometimes it just makes sense for us to look for that 1 time, okay? So last 2 times, good, I got like a minute, 30 seconds. Go quickly. So fortunately, these are the more complicated ones. So the Poisson distribution is basically like the negative binomial distribution, but on a continuous variable. So usually we'll see this in time. So for example, the probability of having a number of occurrences, successes in a given interval. So you might say, for example, how many, what's the probability of having 10 customers walk through the door in the next hour? Like that would be a Poisson distribution. And this would be say, oh, on average, we usually see 3 customers per hour. What's probably having 10 customers per hour? That's the kind of like thing in there. And this is within a given amount of time. So it's a more continuous version of our negative binomial distribution. Exponential distribution is actually kind of similar in the sense of like the number of times this happens in the length of events. So instead of measuring the number of times it happens, it's more like saying how much time goes on until an event occurs. So for example, this is very similar to the Poisson distribution, but like, for example, how much time will it take until the next bus comes? Okay, that would be the probability of an how long this interval will go through. So what's probably waiting 30 minutes for the next bus to go through, or 40 minutes for the next bus to come. So waiting until the new event occurs. And of course, there's some equations we can use. They're very related to something called the gamma function, but basically this factorial part in here, you can see it's a very similar part. This is also, if you do physics, you'll see this like beta decay, or not beta decay, but basically beta will be used as like a decay number. So sometimes you see instead of 1 over lambda, you'll instead see it references beta. So like 1 over beta or beta itself. Okay. Cool. So, hey, that was record time. So I do have to go to another thing, but I'll go ahead and stop my recording here.